Hi, this is KajalZatale and I'm here to explain something about the memory hierarchies.
First, I would like to explain why do we actually need a memory hierarchy. A high processing speed is a key factor of every powerful computer system. The clock speed and maybe the circuit speed, they adds power to the system, but other factors like latency matters a lot. And so designers use hierarchy in order to minimize the latency. The main objective of the hierarchy is to establish a memory subsystem that appears to have a capacity of virtually unlimited memory, as in, say, storage devices, and the speed of the fastest component, as in, say, cache. Now, let me explain something about the traditional hierarchy that is still being followed, that is in the form of a pyramid, as I have made here. At the top of the hierarchy, there are registers. They operate at the speed of the processors. It means that the performance of the processor will be optimum if the information that it has requested is in the registers itself. But there are very limited number of registers as we have less number of space on the chip. So SRAM comes into picture. SRAM is comparatively faster as compared to DRAM, but it has high power dissipation and low packaging density. It's comparatively expensive hence and unaffordable to be used as the main memory. DRAM therefore is used as a main memory. For example, SDRAMs, DDRs nowadays, but they are slower for a MUP and impose latency if directly we use them with the MUP as in on chip. Hence, we use SRAM for the sake of cache. Cache, which is used to store the information which is frequently accessed by the MUP or the processor. It has its own hierarchy like the on-chip cache, the L2 cache and the L3 cache. These are the parameters that, as you can see, which changes as we go from top to bottom into the hierarchy. Now let me explain the memory hierarchy by using an analogy of a central library. Main memory is just like a book which has to be read. Secondary memory is the set of books that we issue and kept in drawer. They are readily accessible, but in order to read a single book, we need to take it out of the drawer and read it and keep it on the desk. Backup memory is the whole central library. It is not really readily accessible, but it is largest in size. Now, why do we need cache? There is a large gap in between the speed of the CPU and the speed of the main memory. We need an intermediate option in order to have a fast data transfer. Roughly speaking, the speed of the CPU referring RAM is around 200 times the speed of the CPU referring L1 cache. But cache has its own hierarchy, which is a long separate story. Herein, I have tabulated various types of memories and various their characteristics, as in the category, whether they read or write, or erasure, as in the modification system that they follow, write mechanism, and whether they are volatile or non-volatile in nature. So why do we need a ROM when we have RAM that can serve our purpose? So basically, after turning on the computer, after booting a system, there are some programs inside the computer that must be active, and so they should be stored at some non-volatile space. And hence we need ROM, because RAM is volatile, as we have seen in the table. But ROM has a problem. Once program is stored, it cannot be modified. So EEPROM came into picture. But there is still a problem because the modification is full chip level. Hence EEPROM came into picture. Herein we can perform the byte level modification, but it was highly unsuccessful as the cost was high, low density and unreliable. Hence Flash was invented. In Flash, there is a block level or page level modification that can be done, and hence it's working well. Now let me explain the SRAM architecture. In an SRAM, as you can see, this is a SRAM cell array which has many cells into it. The row address and the column address are given separately to select a particular cell. Here's a sense amplifier, a pre-charge circuit, and these are the input-output lines. The data can be read by the input-output lines or can be forced inside the cell using the input-output lines. Now let me explain the working of every single cell. When the word line is activated, the bit lines are connected to the inverters. It has a large capacitance which needs to be precharged, and hence we need the precharge circuit. The precharge circuit, they balances the capacitances, as in they charge them to a particular voltage. Now, if we give a bit line as 1 and bit line bar as 0, this line will be discharged and this will be charged. So the precharge there will be an imbalance in the precharge voltages, which is sensed by the sense amplifier and is balanced by charging this line and discharging this line. Now let me explain something about the DRAM architecture. As you can see, these are the DRAM cells. It has a single transistor into it with a capacitor. These cells are divided into two parts, as in the top half and the bottom half, and a single sense amplifier connected to it. As in, if there are, suppose 128 cells in a column, 64 will be divided in the upper half and 64 will be kept in the lower half. Here is a single DRAM cell. It has a single transistor and with a capacitor. When the word line is activated, the bit line is connected to the capacitor, and if there is one that is if it is charged, it is 1 that is stored, and if it is discharged, it is 0 that is stored. Now, why is it called as a dynamic memory, dynamic RAM? Because the charge that is stored inside the capacitor, the charge here is stored inside the capacitor, and a capacitor tends to leak. Therefore, if we are going to wait for a long time without refreshing the data, it may happen that the information can leak completely. That is, 1 can be changed to 0, hence dynamic. Now, coming to the secondary storage, the next level, it is not really directly accessible to the CPU, as we have seen in the library analogy. It is the set of books issued and kept in the drawer. So in order to read it, first read the book, you need to take the book out of the drawer, keep it on the desk, and then read it. As in, you need to take the data, keep it in the main memory, and then you can read it. It is used to store data or instructions which are not really actively in use. There are many examples like hard disk, magnetic disk, the tapes, DVDs, floppies, but SSDs are the ones which are rocking because of the features like low power consumption and less heating that is required. They are reliable and they are faster as compared to that of the hard disk. But if the information is not found in the main memory, that is, if we need to access the secondary storage, the access is too slow, even for the fastest SSD, as compared to that of the main memory. In this case, the system performance is degraded. So, a solution is a virtual memory, which is a separate big chapter, and so I won't be going deep into it. Now, let me move to the next generation technologies. They are emerging, but they are not included yet into the hierarchy. First of all, I would like to explain this graph. Herein you can see that the core count in a multiprocessor system, the core count is doubling every 2 years, while the DRAM capacity count is like doubling in say 3 years, which is not a good thing. DRAM is almost meeting its limits because the need for the capacity and the bandwidth is always greater, and the main memory energy or power is a key system design concern which is not being met, and it has already reached its scaling limits. So DRAM is now no longer a good option to be used as a main memory. Some of the new technologies like the STT MRAMs, the memristors, the ReRAMs, 3DX points, NRAMs, they are promising, but in order to come into the hierarchy, they need to hit the market with a reasonable cost. In this way, there is a thumbs up from my side for the memory hierarchies, as it is improving the access time and the overall capacity of the memory subsystem. These are the references that I have been using for making this presentation.